using angle bisectors. And we're going to start with theorem 5.7, which says concurrency of angle bisectors of a triangle. Now, I'll remind you that concurrency basically means intersection. Concurrency is the spot where all the lines intersect. So the angle bisectors of a triangle also can intersect. Since each triangle has 3 angles, that means there could be 3 angle bisectors. So let's look at this triangle here. This is triangle A, B, C. This line here is an angle bisector. And this over here is an angle bisector. And this line over here is an angle bisector. The 3 angle bisectors meet here. That is a point of concurrency. And in this theorem it says the angle bisectors of a triangle intersect at a point that is equidistant from the sides of the triangle. So this point where all the angle bisectors meet is equidistant to all the sides of the triangle. So these blue lines are all congruent and perpendicular to the sides. Okay. The point of concurrency of the 3 angle bisectors of a triangle is called the incenter. So where all the angle bisectors meet, right here, is called incenter. The incenter always lies inside the triangle. Because the incenter P is equidistant from the 3 sides of the triangle, a circle drawn using P as the center and the distance to one side as the radius will just touch the other 2 sides. The circle is said to be inscribed within the triangle. So if you draw a circle inside the triangle, the incenter will coincide with the center of the circle. And these segments here will be the radius of the circle. We'll get more into circles in chapter 10, but it's important for you to know that when you draw a circle inside of a triangle and the circle touches each side of the triangle, that's called inscribed. The circle is inscribed within the triangle. Now let's use the theorem on concurrency. In the diagram, N is the incenter of ABC. So this is the incenter, where all the angle bisectors meet. Find ND. So they want us to find the length of ND. Well, remember, all of these are congruent. They tell us this side is 16. We want to know what ND is. Well, they give us the length of one of the angle bisectors. This angle bisector here is 20, and this piece here is 16. If you look at this, there's a mini triangle here. This is 90 degrees, so the other side is 90. So now we have a triangle that has a slanted height of 20 and a base of 16. This blue segment is what's missing. Since all the blue segments are congruent, if we find what this blue segment is, we'll automatically know what this segment measures, ND. Well, let's check out the solution. So we use Pythagorean theorem to find the missing angle. Now you may have used this in your algebra class, but if not, the Pythagorean theorem is a handy formula in order to find the missing side length of any triangle. So if a triangle, for example, it only works for right triangles. If you have a right triangle, and let's say you call the legs of the right triangle A and B and the hypotenuse C, A squared plus B squared equals C squared. That's what it says here. A squared plus B squared equals C squared. So here the C is 20. The B is 16. And we don't know what A is. That's what's missing. So we do A squared plus 16 squared equals 20 squared. And that is 20 squared is 400. 16 squared $256. Okay, we subtract 256 from both sides. And that gives us A squared equals 400 minus 256. $144. Now, since A squared is 144, we have to take the square root of both sides, and we get A equal to 12. So this missing side is 12. So that means this side here is 12. And since all the blue segments are the same, segment ND, the one that we're being asked and that we're looking for, also has to be 12. Okay, and let's see if that's correct. And it sure looks correct. Yep, there it is, 12.